in the last class, we saw about the errors. Okay, every measurement, any measurement of a physical quantity will have an inaccuracy associated with it. That we called as a error, that we found as error, and then we saw the error basically comes in two types. One is systematic error, and then the random error. And the systematic error can be reduced because by changing your being more careful and having a better instrument and all. But random errors, you have to live with it. It will always happen. It will be there. Okay. And then we also saw the the what is so because of the errors means when you do the experiments multiple times. Okay. Suppose you want to measure a quantity multiple times. Okay, so then there none of all the quantities, suppose 100 times. 100 times this value is going to be slightly changing. So then you need to find out what is the most probable value. And we saw that is taking an average. The average of, suppose you do the n times you do the experiment, the average of the n experiments will give you the most probable probable value of that most probable measurement. And then we saw then the absolute error, we define the absolute error, that's the deviation for every measurement from the most probable measurement. And then we found, so for, there will be, suppose if you did n experiments if you have done it, so the n experiments will have the n absolute errors, the average of all those n absolute errors is the actually your error in the most probable value. And then we saw about the relative error and all those things. Okay, so now, let us think of an experiment. Okay, I'm trying to take some experiment which is given similar in your book. So I am going to have, I'm going to consider a electric circuit. Okay, so let us say, and I'm going to have two resistors, something like this. It's an electrical circuit, right? So the current means it goes from here to here. Okay. So and then so this is some voltage V. I'm asking you, what is the voltage across this resistance? So let us say this will be V1. This is the experiment we are doing. So what we need to find the voltage, what all we need, so we need we have to know the current passing through it to the circuit. So you will add an ammeter. Okay. And then I need a voltage across it. So you need to know what is the value of the resistance also. And then you need to measure the voltage also, right? So voltage will be maybe some voltmeter, we will have something like a voltmeter we will have. So let us consider a case. Suppose I wanted to find out, we can consider this problem as a different type of problem. Suppose I wanted to find, I don't know what is this resistance. I want to find out what is the voltage across this resistance. Okay, so all I know is I'm going to have you, so the ammeter is going to give me the current and resistance I know. So I have to find out the voltage. So we know the voltage across this resistor R, let me write, V are equal to how much? I into R, correct? That's the voltage. Now this ammeter measurement, I is going to have, it's this ammeter I told you, all ammeter will have an error, correct? So when there is no current, it won't remain at 0, there will be a small shift. So I will have one I plus delta I. Am I right? And similarly resistance, when I say resistance also, no resistance can be, see I'm saying in physics, any measurement, no measurement is exact. Always there will be an error associated with it. So it is not going to be R, it should be R plus or minus delta R. Now the question is, so because my current is having an error, my resistor is also having an error, so the voltage, I keep a switch and do the same experiment some 100 times. Okay, so what am I going to do? I am going to add up a switch and keep pressing the switch for 100 times, and every time I am going to measure the voltage. I am not going to get the same voltage, the voltage is going to differ because of the error associated with the current as well as the error associated with the R. Now the question is, what is the error associated with my voltage? This one. Okay, because now there is not a single, there are two errors. Okay, this is a combination. And similarly, I can have another experiment also. So suppose I have another way, I am going to yeah. So or if you have suppose other way, I want to measure the resistance here. I don't know what the R is. Then I will connect this voltmeter here, get the voltage, okay, get the voltage, and then I can measure the R. So this is going to give me V plus delta V. I know your R is nothing but V by I. So R will have an error because of V will have an V plus minus delta V and I plus minus delta I. Okay, so my measurement of resistance will also have an error because of the combination of these error in those instruments. So this is that time we can see it comes more like a product, right? I into R. You may get a different way also, additive also. For example, I am having a resistor in series R1, R2. I want to find out the equivalent resistance. You remember last time we did resistance, equivalent resistance is what? This will be equivalent to a single resistor of value R, which is equal to R1 plus R2. Now R1 will have plus minus delta R1. R2 will have plus minus delta R2. So what will be my delta R? Okay. So what am I saying is, so when we have the errors in combinations, so what will be the resultant value you are going to obtain? What will be its error? So that is what we call as a combination of errors. So let us this is the example of how this combination of errors will come. So let us see one by one. Okay. First, let me take up a simple case of when the errors get added up. So that means I am going to have a quantity, something like a resistance in series. So we will have, so I am having two quantities, two measurements, something like R1, R2. I will not call this R1, R2. I am going to call it as A and B. And because there were the two quantities A, my final quantity, what I am going to measure will be Z equal to A plus B. Suppose this is what we are having. So in our case, equivalent resistance. R1 plus R2 gives equivalent resistance. So that problem I am writing like this. Now your A will have an A will have a error. Am I right? Plus minus delta A. Similarly, B will have B plus minus delta. Oops. See, I am telling A and I am writing B. Okay. And now the question is, so what will be my delta Z? So it is not very tough. So we have Z equal to A plus B. Therefore, Z plus delta Z plus minus the error will be the A will have an error A plus minus delta A plus B plus minus delta B. So this will be A plus minus delta A plus B plus minus delta B. So this combination of these two errors is going to give one Z value plus the error in the Z. So if I open the bracket, so what will we have? A plus B plus minus delta A plus minus delta B. Okay. So and A plus B is what? Z. So this will be what? Z plus minus delta Z. Okay. So A plus B is nothing but by Z. Am I right? So this Z and this Z will cancel off. Correct? If I take this Z here, minus Z. So what we are having, so we can write this as, so plus minus delta z will be equal to plus minus delta a plus minus delta b. Now if you remember, when we are telling about error, so this I can write it as just like a delta z. So delta z, let me find out. So if you remember, when we write the absolute error, we wrote it as a magnitude. So all delta A mean, if you remember in the last class, is all a magnitude. They are all always positive quantity. And we write that as a plus minus. Correct? So similarly, so here again this is a positive quantity. So we are writing it as a plus minus. So the delta Z will have, what are the possible combinations? Delta A plus delta B. Yeah, delta A minus delta B minus delta A minus delta B and then minus delta A plus delta B. So among this, which will have the maximum magnitude? Maximum mod of that. So we are having, so this and this are more or less same. Am I right? Because this is minus delta A plus delta B. So this is the quantity, and these two quantities, the magnitude of these two quantities will be always smaller than this. Am I right? When we are saying about error, we should always give what is the maximum error you are going to get. You may get something smaller also. Okay, that doesn't matter. When I speak about accuracy, my measurement is accurate up to this number plus minus this. And the plus minus this has to be always a maximum. I can't take the minimum value and cheat the people. Okay, so that means my error, the magnitude should be delta A plus delta B, not your minus. So then I can write, so then your delta Z equal to delta A plus delta B. Okay, and so then this will have a positive negative sign. So in your final measurement will have Z plus minus delta Z. Okay, when it becomes plus, you are taking this error. When it becomes minus, you are taking this error. So it doesn't matter. So this is the way. So always when you write an error, we never put the sign. We always take the magnitude. So this will be always positive. So when you take a magnitude, this both also will become same. Fine. So let us try to find out in case your experiment is such that Z is not A plus B. Z is A minus B. What is that? Z equal to A minus B. So then what will be the error associated with such a combination of errors? Okay, there will be error associated with A and B. So then what will have? So when I wanted, so because of the error in A and B, my Z will not be exact. It will have an error, that plus delta Z, and that will be error due to A minus error due to B. So let us open it. What we have? A minus B plus or minus A delta A, and this will be minus plus or whatever, it doesn't matter because we are taking plus or minus only. So this will be again plus or minus of delta B. Right? So this will be what? A minus B is Z. So this and this cancels, therefore delta Z will be, okay, this is plus minus delta Z will be equal to plus minus delta A plus minus delta B. So again the same argument comes. We have to take the maximum value, correct? So when the maximum, you always take the positive. So your delta Z should be equal to delta A plus delta B. So this is the error you get due to the addition of two quantities with error. The resultant error due to the addition of two quantities with addition or subtraction of two quantities with error will be this. If you have a third quantity, it will be that also, delta A plus delta B plus delta C. It keep going. Okay. And okay, so now let us go for the next case. That is your multiplication. So you remember we said V equal to I into R. Okay, so that's the multiplication of errors. So when you say multiplication of error, what you normally write is a relative error, not this delta Z. We will write a relative error. I'll show you how to do it. And yeah, once you know the relative error, you can actually find out the actual error also, because that will multiply with the most probable value. So we are having a new measurement where Z equal to AB. So then what happened? So now A is also going to have an error, B is also going to have an error. So because of that, what we will have, Z will also have an error, okay, and that will be A plus minus delta A into B plus minus delta B. Correct? Let us open up. What this will be? AB plus, so this one, plus minus A delta B plus minus B delta A plus minus delta A delta B. Correct?
So that should be plus delta A plus delta B, because even if it's minus we can cancel.
No. When we take an error, it is not necessarily always. See that you are doing with the, yeah, so you are assuming, so minus becomes, plus becomes minus becomes plus.
No, plus will also become.
Yeah, plus also becomes plus, and minus also becomes plus. That is not the case here. Okay, it may happen delta A will be positive, delta B can be negative. Understand? Don't go into what the mathematically when we do. Don't go into that model. Okay, because there can be an error. This what it means is it can be positive or negative. It is there. What happened? That you can do only under the case if this is positive error, this also to be positive error. If this is negative error, this also should be negative error. Here we don't have that condition at all. This can be positive and this can be negative. So it should be always plus minus only. Okay. And okay, so let us write. So this will become, so this AB will be Z. Am I right? Z. So let us try to take the Z commonly, or okay, let me keep it AB only. So AB, and I am going to take Z commonly outside. So when I take Z commonly outside, what happened? 1 plus minus delta Z by Z. Am I right? And here I am going to take the AB commonly outside. So when I take AB commonly outside, what will I have? 1 plus minus. So when divided by AB, AA cancels. So delta B by B plus minus delta A by A plus minus delta A by A into delta B by B. Correct? Now, you know what is this delta A B by A and delta A by A? They is called as a relative error. You remember? Okay, the relative error will be always small. You remember it became 0.01, then that's why we always express it in percentage. So this will be very small number. So relative errors are very small numbers. Now, when two relative errors are multiplied, that will be further small. Am I right? So what happens? So you are going to add 1 plus 1 relative error. So I will tell you, let us put up a simple case. So this will be what? Let us take this error equal to 0.1 for simple. So this is also making 0.1. So this will be what? 0.1 into 0.1, that will be 0.01. When I add them all, what will happen? This will be 0.21. Am I right? This plus this plus this. This I can always write approximately 0.2. Okay. And if you see, if I go it further and further smaller, this is I made it for 10% error. If I make it further smaller, it will become much smaller. So then what happens? So this quantity will be always smaller than these quantities. So I can neglect this quantity. You understood? Because that number is small, it doesn't matter for me whether it's 0.2 or 0.21 or 0.2. Because anyway, I'm telling my error is at 0.2. So now if it go by 0.21, it doesn't matter because already it's 0.2 times error. Okay, that you will see it in the next time. The next section you will see something called significant digits. There you will see what the number you will take up to where. So this will be so I can write it like the last two product I can neglect and I will get this. So now I will write what I am going to do is, so AB is Z, am I right? So then AB becomes Z, so this cancels off and then 1 also cancels. So finally we are getting plus minus delta Z by Z will be equal to plus minus delta B by B plus minus delta A by A. The same argument comes. You have to take the maximum magnitude. Okay. So therefore, if I write delta Z by Z will be delta A by A plus delta B by B, and that's going to have the maximum magnitude. So this is the error. And interestingly, if you have a division of quantities, you have the measurement Z, which comes a division of two individual measurements, A and B. So what I mean, so Z equal to A by B. We will not do it because it needs some more calculations. That means you have to use some theorems and all, some series theorem whatever you have to use. We will not use those theorems. So what I will say is, in a simple way, this will have, you can show this also will have the same error like this. So even in the division also, what will you have? Delta Z by Z will be delta A by A plus delta B by B. Okay, so that comes something called as your binomial theorem, and you have to use it. Okay, so I am not going to use those theorems. That you will, when you, I think, I don't know, maybe possibly next year you will learn, or maybe in your BSc you will learn it. Okay. So yeah, tell me.
Plus minus.
I told you, yeah, correct. This is plus minus, but you have to always take the maximum magnitude. You got it? Yes, this will be plus minus. This is also plus minus. But the moment if I take minus and 1 is plus, then it's going to be not the maximum. Maximum magnitude will be plus and plus, and minus and minus. And minus doesn't matter. When I'm going to take always the modulus of it, so this will be plus only. You got it? So that's why we don't have the plus minus. So this is what the combination of errors. So when the two quantities are addition, the errors, the uncertainties will get added. So that means Z equal to A plus B or A minus B, delta Z will be delta A plus delta B, even though it is plus or minus. In the case when it is a multiplication or division, the relative errors get added. That's what you have to remember. It is not delta Z equal to delta A plus delta B. Delta Z equal to delta A plus delta B when there is some addition or subtraction of measurements with errors. So when there is a multiplication or division of measurement with errors, the relative error will get added up. So this is, you should remember it always. The problems, there can be problems based on this. Suppose I have I have power. So let us try to see, try to find a condition. Suppose I have a quantity A, and my Z is Z cube, A cube. And my A will have an error, then what will be my error in delta Z? Okay, it is tough, simple. What? Z equal to what? A into A into A. When there is a product, what gets added up? Relative error, correct? So delta Z by Z will be delta A by A plus delta A by A plus delta A by A. Therefore, this makes it 3 times delta A by A. Okay? Or if your Z is equal to A power n, then delta Z by Z will be equal to n times delta A by A. Or there are many components. Usually in experiment it is, suppose you have a quantity A to the power of P, B to the power of Q, to the power of, say, something like C to the power of n. Tell me what will be the relative error? So this will have P into delta A by A. Multiplication is always plus Q into delta B by B. Doesn't matter division. I told you. It's always again the same thing. It goes, the relative error gets added. Plus, I wrote it as N. Okay, fine. We can write it as R, P, Q, R. Correct? R into delta C by C. You got? It's clear? So this is the way you find the error. Okay? So let us, your question. What was your question? Z equal to A power 1 by 2. See that formula what we said, Z equal to A power n. So then your delta Z by Z will be n into delta A by A. Okay? Because we found, because that these are basically product of A, and product even when the quantities are in product, the relative errors will be in addition. Correct? So, and there we always consider n to be an integer. So now your question is when n is equal to half. Okay, so this, the same rule applies here also. Okay, but that comes as something called as differentiation. I guess you will have in the mathematics, I think you will have in the maybe this year or next year you will have. So what is something, if you have a quantity x to the power of n, if you want to differentiate it, okay, so what am I having? I am having some quantity z equal to x power n. When I differentiate, differentiation is similar to your delta. So when I differentiate it, this will, we write a d of z. So what the formula will be, n into x into n minus 1 dz. Okay, so dx. This is x here. Okay, the d we can always convert it as delta z, and delta x, you can write it like this. So from here, so if you write n equal to half, right? So then this becomes delta z will become half x to the power of half minus 1, that become minus half, correct? And delta x. So I am going to multiply, so this delta half minus half, I can write 1 by x minus half. So this will become x power half. I will multiply above and below with x power half. So this will be x. And we have, what we will have, 1 by 2 into x power half into delta x by x. Okay. And what is x power half? X power half is our z, right? Delta z. That's what, because we took n equal to half, right? So this will become z. So delta z by z will be equal to half into delta x by x. And that's what the same rule is. You understood? Okay, so anyway, you don't have to really bother about it, this one. So this rule is this z, when z is a power n, which is equal to 1 plus and this is satisfies for square roots also. That's what you have to remember it. Okay. Significant figures. So now what this means? So we said we have the measurement and we have the error. Okay. So the point is, when I write a quantity, okay, so I made a very precise measurement or something up to certain digits, say 2.345678 or something like that. And I know most of the last digits are lost, come into the error. So I don't know, if I give someone to measure the same quantity, he will find a different answer. So then, up to what digit I can write? That's what you call as a significant figures. So I take a very simple example. So something similar to the example given in a book. I'm giving you a small stick to 4 people, and I'm asking you to measure, give your scale, with the scale what you have, I'm asking you to measure with your own scales. So then 4 people, the stick measurement, let us say one said the measurement is 5.1. So this is the number 1. He gave it, this is the measurement of the stick. The number 2 again gave 5.1. Number 3, he had, we don't know what scale he used. So he said, no, it is 5.2. Okay? We can't go anything beyond that, because if you remember in the scale, centimeter. Okay? These are all I'm saying. Because your scale, normal scale, your least count is 0.1. Correct? You can't go. So the error can be, people can make a mistake in 0.1. He won't tell it's 0.5, of course. The least count is point only. The difference can be always between the 0.1. So it may be 5.1, 5.1, 5.2. And the 4th person may again use the same thing, 5.1. So, and you are giving me these values. So now I wanted to say, okay, so what is the length of the stick I am having in my hand? So, so then what will I do? We saw. So then I know each measurement is having a difference. So then what will be the most probable value? That is the average of these two, correct? So let me call the length as L. L will be L will be the most probable value, will be the average of all these numbers, correct? That is 5.1 plus 5.1 plus 5.1 plus 5.2 divided by 4. How much this will be? Tell me. 5 point 20. Tell me 20.5 divided by 4. That is equal to 5.125. Is that right? Correct. 5.125. So I will call the length is 5.125. But now this is not the correct way. Then okay, now I know this 5.125, the difference will be, then I take the difference between them, that gives me the error in my maximum probable value, most probable value. Now, but this is not the right way of presenting, because I know none of you gave me up to this precision. Correct? You all gave only up to here. Right? So none of you gave up to this precision. So then I should not use all the digits. Some digits I have to cut, because this will misguide the people. When you tell me the when I give you the scale, length of this stick is 5.125, everyone will think you people had a very high-tech scale which goes up to the 0.001 centimeter you can measure, something which is not correct. So then I have to stop at these values. I should not give anything beyond some digit. Okay. So what is the digit? How to do that? What to the way? That's what called as significant figures. What the significant figure is, of course, you will get more or less close to what the value, correct? So, and what you should see is, which is the significant same figure you have. See, for example, so we are having, let us take the first figure, 5. So 5 is common in all. Okay, so I will add 5. 5 is one of the significant figure. So let us go for next one. 1. 1, is it common? All for same? No, because this is have a difference. So then the moment I get anywhere else there's a difference, I will stop with that number. So the significant digit is and 1. So these numbers I am not going to use it. So in that case, I will write, even though my measurement comes out, the most probable value, I will write it as 5.1. You got it? So, significant figures is the figures which appears same in all the measurements plus one more digit. In the most probable value, when you take the average of it, go up to the figures which is common in all the measurements and stop with that where they differ. Okay, so that's what you call as your significant figures. Okay, if the significant figures, if you have a large number of significant figures, that means that measurement is precise. If you people have used better rather than using your stupid ruler, if you got a very precise measuring one, you people would have got a better measurements. Am I right? So then I would have got still, I mean, the equal magnitude digits will be there for more number of values. So then it will increase. So what happens? So the total number of significant figures, how many significant figures you are able to get, that decides the accuracy of your experiment. Okay? Okay. So there is something, the rules for determining the significant figures. So the first one is all the non-zero digits are significant. That's obvious when you wrote it. Nah? So for example, what they given example is the volume. So if you have measured some volume, what I'm saying, I want to measure some volume of some liquid. So, and I gave it to, I asked you to measure, then I asked you to pass on to everyone. Everyone has measured. So then you got an average, then you got a number, then I take the average of all the numbers and then I got a most probable value. And then I know up to what is the figure which is not changing in all your measurement. I take one after that, that gives me the significant figure. Okay, so for example, what they say is, so if you have so the example they give is 178.43 centimeter cube. So once you wrote it down, this all figures are significant. So what they say is all non-zero digits are significant. Okay, so that means suppose if you have something 0 here, oh, that will come later on. So if you can't, means all these digits are significant. That's what we're repeating the same thing what we had done earlier. And this has to connect with the second point. So here the significant figures are 17843. All the zeros, second point, all the zeros between two non-zero digits are significant. Example 165.02. Now you can't throw away 0. Oh, this is 0. So this is not significant. So your significant digits are 1652. No, 16502. They are also significant. Okay. And there's a very interesting point comes. If the number is less than 1, the zeros on the right of the decimal point and to the left of the first non-zero digit are not significant. Okay. So the point is, so if you have a measurement something like 0.001521, these digits, the right of the decimal point and before the first significant figure, they are non-significant. Okay, so here the significant figures are 1, 5, 2 and 1. How we are going to represent the number, we will see. That number has represented in the scientific notation. We will come there. Okay. Yes, 10 to the power of minus 2. So something like that we have to write. Okay, but there is your book has a different method, but people generally use different ways also. Okay, and the fourth point is the zeros on the right hand side of the last non-zero number are significant. Okay, and this is very interesting. But this number must be written in with a decimal point. Okay, so for example,
2.0.
What they are saying is 1.500 or for example, other one 0.01500 have both of them have 4 significant digits. That means what? 1, 2, 3, 4. 1, 2, 3, 4. I told you, any zeros after the decimal point we don't consider. But remember, this 0, 0 is also significant. And this is not, this may actually confusing, it'll be very confusing. So if you remember last measurement, what we did with, suppose we take the length of the stick we measurement. What is the value we got? 5.125, right? So then we made it as a significant digit and then we took it as 5.1, correct? Now you can't simply draw 2 zeros. See, I got significant up to 2 zeros. Okay, this is not allowed. So what I'm saying is, if all your measurement, what happened, you got, so suppose for example, when you take an average of all your measurements, let us take this way. So for example, if I have one measurement is 5.1000, okay, 1.001, very precise measurement you people are doing. And another one is 5.100, okay, let us write 0, 1. And another one is 5.1001 and everybody else got 1.001. So then here what happened, when you take an average will be obviously, because next time is 0. So when you take a most probable value and when you take the significant figures, what you will get is 5.100. You got it? 5.100. So now here these two zeros are significant. You didn't add by hand. Okay. So therefore in this case, the zeros are also significant. Otherwise, that's the actual zero is there. It is not that you don't know that value. If you don't have this precision, you got only up to 5.1. Oh, I made it 2, 3, 0. See, I'm precise to up to that. So you can't do that. Okay. So that's what these zeros has a meaning. So that's what they say. Any zeros in the trailing zeros after the decimal point, they have, they are significant. Okay, so here, because the previous one is okay, because you can always write it as in the exponential scientific notation, which you will see next one. Okay, and that's what your problem is. Yeah, that's what they say. See here, for example, they give a nice example. So you made a measurement, and the measurement gave you L equal to 125 meter. Now I can't convert this into centimeter. 125.00 centimeter. Yeah, see, these two zeros are also significant. You got it? Here what happened? Of course, here the significant digits are 3 figures. Here also they are 3. Because you just multiplied by 100. You never know that what is the value beyond it. Correct. Your actual measurement be your actual measurement will be 125 point say something 3. Okay, but because of your precision, you never got this number. So you round it like this meter up to significant digits. Now when I multiply with 0, you take 12500, but actual number will be 125.33. Okay, this you don't measure, so it is not a significant. So here your significant figures will be 125 only. Okay, so these are all, this cheating is not allowed in physics. Okay. Correct? So yeah, that's the other interesting part. What they say is, to avoid the ambiguities in determining the number of significant figures, it is necessary to report every measurement in scientific notation. Okay, and that is it's in powers of 10. So by using the concept of order of magnitude, we will see that. Okay, so yeah, but only thing is, in your book they have taken the, okay, the scientific notation is what happened, any number, try the scientific notation, you read about it? Okay, yeah, fine. So that is something like that. You have a mantissa into 10 to the power of something, correct? What they have written is any number, so they write it like in this form, a into 10 to the power of n, where a, see in your book, I don't know, this order of magnitude, what they say is a will be 0.5 less than or equal to a less than 5. But most of the cases we don't use like this. We usually take it from 1 to 9. So your will be 1 less than equal to a less than 10. This is all the way we can write it. Okay. I don't know why in a book there it is 0.524. Anyway, it doesn't matter. This is the way you have to write. The rest of all the quantities you can. So for example, let us take an example. Let us do an example. What are you going to? Okay, the same example. Radius of Earth. How much? 6,400 kilometer. So if you want to write it in scientific notation, what happened? So if you want to follow this method, so this will be written as what? 6.4. Oh, sorry, no, it should be less than 5. Now 0.64. 0.64 into 10 to the power of
3.
3? 4. 4 kilometer. Okay, so this is what the given. Suppose, but anyway, most of the cases we use this form. So in that case, it becomes 6.4 to 10 to the power of 3 kilometer. Okay, I don't know. In your book, they written this, so you have to follow this. Okay. Yeah, here what happened? The order of magnitude is 0.64. The order of they have written in they have written in meters. So then what happens? 0.64 into 10 to the power of 4 into 10 to the power of 3. Correct? This meter. So this will be 0.64 into 10 to the power of 7 meter. Okay, so you can see here that ambiguity was not there. Centimeter to meter conversion, all those meter to centimeter, we put 2 zeros. They all go into the 10 to the power. Okay, so then what happens? So this, then they call this 7 is the 7 is the magnitude. Okay, this power, and this is your what you call this is what they usually call as a mantissa. Okay, and how many significant figures this has?
2.
Yeah, only 2. Okay, so this is the magnitude. You should always write in the order of magnitude notation, scientific notation. You will do that. Okay, so and that's it. Okay, so then there are some exercises given in your book. Attempt all the exercises, and if you have a problem, we will see it on the board. Okay.